Everybody, the idea of this problem is to actually compute some missing digits without actually directly computing the decimal expansion or the decimal representation of 17 to the 6th. That would spoil all the fun, right? You could use a calculator or do that by hand. That's tedious in my opinion. So we're going to try to figure out what the missing digits are with this given information. We're given that it's an 8-digit number with 8 distinct digits. Okay, so since there's 10 decimal digits, there's clearly 2 missing digits is the way we're wording this. Okay, now let's just talk. This is an example of a sum of the digits problem where that result, a particular result regarding the sum of the digits is handy. Now the sum of the digits for this number 417, which is not even related to this problem, would be 4 plus 1 plus 7. Okay, and of course that's equal to 12, right? So the sum of the digits of the 3-digit number 417 is 12. SOD stands for sum of digits. 4 plus 1 plus 7 is 12. Now it turns out this result right here is a big result towards solving our particular problem here. It turns out that any number, not just 17 to the 6th, is congruent to the sum of its digits mod 9. Now I won't go through a proof of that, but it follows almost immediately from the fact that 10 raised to the n power, where n is any natural number or any non-negative integer, I guess, is always going to be congruent to 1. Okay, and that's very easy to see, mod 9, right? Mod 9. And think about it, if n is 1, you would have 10 minus 1, which is 9. If n is 2, you would have 100 minus 1, which is 99. 10 cubed, 1000 minus 1 is 999. So this is very clear. And since 10 to the n is present in the decimal expansion of 17 to the 6th, it follows that this number would be congruent to the sum of its digits mod 9. Okay? Now, let's keep going. Now, this isn't so clear right here. 17 to the 6th is congruent to 1 mod 9. Well, it follows from the fact that 17 itself is congruent to 8. Now, y'all, we are assuming mod 9 here. I won't write that down. But 17 is congruent to 8 because 17 minus 8 is 9, and 9 is divisible by 9. This means that you can treat congruences just like equalities in many regards. So 17 squared is congruent to 8 squared, which is 64, right? It's congruent to 64, but here's where it gets fun. But 64 is congruent to 1. And you can see that 64 minus 1 is 63, and 9 times 7 is 63, right? But notice that 17 to the 6th is, by laws of exponents, is equal to 17 squared. Quantity cubed, right? Laws of exponents, 3 copies of 2 copies is 6 copies. All right? So there you go, folks. That's why this turns out to be a fairly useful result, because these 2 congruences, like again, they behave just like equality. And so that means the sum of the digits of 17 to the 6th is congruent to 1. Now that gives us quite a bit of information actually. So the sum of the digits, certainly 1. 10 leaves a remainder when divided by 9. 10 leaves a remainder of 1 when divided by 9. 19 leaves a remainder of 1 when divided by 9, and all the way across, all the way out, 28, 37, they all leave. For example, 37 would be 3 times 12 plus 1. So all these numbers leave a remainder of 1 upon division by 9, which is what this congruence means. Okay, now some of this stuff, we can eliminate a lot of these results quickly, and note that the sum of the digits can only be 28 or 37, and that follows pretty quickly. The sum of all the digits, and I exclude 0 because it doesn't change the sum, but notice that the digits 1 through 9 add up to 45. That's easy to prove. That's a triangular number, you know. But anyway, these are the only possibilities, and that's because of these very obvious statements down here, right? The minimum is going to occur if you do include 0, all the way up to 7, leaving out 8 and 9. The maximum is going to occur if you do include 8 and 9. Now notice that 37 itself this 37 would imply that 0 and 8 were the excluded. Okay? I mean, that would be the answer to our problem, right? Because that's easy to see since they all add up to 45, right? So 0 and 8 would be the answer to our problem if this was our only choice. But notice that 28 also leaves a remainder of 1, right? Now notice, again, that's this circumstance right here. This would imply that 8 and 9 are excluded, right? So these are the only two possibilities, folks. Now, how do we resolve this? At this point, it seems unresolvable. But one thing you can consider also is the sum of the digits modulo 10 to find out what the last digit is, and that might lead us to, we would gain more information that way. So let's take a look at what happens when we do 17 raised to the 6th power. Okay. Let's look at this modulo 10, right? Now, y'all, why is mod 10 important? Because mod 10 gives you the remainder, right? Like, for example, 18 divided by 10 leaves a remainder of 8, but 8 is the last digit, right? So this helps us figure out the last digit, okay? Of any number, not just 17 to the 6th, right? All right, so let's see what we can do towards solving this problem. Now notice 17 is congruent to 10. Let's just start writing over here. 17 is definitely congruent to, 17 is congruent to 7 mod 10, right? No doubt about that. So that means that 17 squared is congruent. Let's see here. 17 squared would be congruent to 49. Right, what did I do? I just squared the 7 right here. But notice that this is congruent to 9, right? Okay, and if you keep going with this, you'll eventually see what happens right here. 17 squared, which one do you want? We can actually try 7. If you want to, we can go ahead and just do 17 to the 6th. 17 to the 6th is congruent to, since we cubed this, we have to cube this, right? Is congruent to 9 cubed. Right, but this is an easy calculation, right? It's easier than 17 to the 6th. This is equal to what? 9 cubed is 81 times 9, which is 729. See, which is congruent to 9, right? So you see, that means that the last digit of 17 to the 6th is 9, okay? So that means this is the last digit of 17 to the 6th. So that means we would exclude this possibility and start, this one does include 9, right? And so we have to, 9 would be excluded. 9 is included in this, this statement right here implies that 8 and 9 are part, or the digits, right? Or in the digit representation. And so we found out though that 17 to the 6th ends in 9. And so that means this is going to be our answer right here. It would be 0, 8. Okay, 0 and 8 would be the digits that are excluded. I hope that was clear, folks. Slightly confusing. And a lot of you might be saying, well, you might as well just do raise 17 to the 6th manually, and that's true. I mean, I think it's tedious. 17 to the 6th is a very tedious calculation if you just do it by hand without a calculator. But anyway, we've just determined that 0 and 8 are the missing two digits, all right? 0 and 8. Hey, y'all. That's how it's done using modular arithmetic. And thank you for viewing.